Welcome back, everyone, to another explainer. Today, we're getting right into the nuts and bolts of a really specific but highly rewarding project. We're sizing and wiring a 10 kilowatt on-grid solar power system. Now, installing a 10 kilowatt setup, yeah, that's a pretty massive investment. But when you do it right, it's the kind of investment that can absolutely slash your monthly electricity bills and seriously shrink your carbon footprint. In this explainer, we're leaving no stone unturned. We're going to use the data from our source material to walk through everything, from nailing the precise component selection to that crucial final safety testing. Okay, let's dive into this. Because, looking at a fully completed solar installation can feel completely overwhelming. You've got wires going everywhere, massive boxes just humming on the wall. But how do you actually wire it all together from scratch? Well, think of this explainer as your personal step-by-step blueprint. We're going to logically trace the exact path of the electricity, starting all the way up on the roof where the sun hits those panels, down through the safety mechanisms, and right into your local power grid.
So here's our roadmap for today. First, core components uncovered. Second, doing the solar math. Third, wiring the DC side. And finally, connecting the AC grid. All right, section 1, core components uncovered. Basically our ingredients list. So, before we can wire anything together, we obviously need to gather our ingredients. A complete 10 kilowatt setup relies on 9 primary components: your solar panels, the inverter, the mounting structure, the DC and AC distribution boards, the energy meter, cables and connectors, the AC disconnect breaker, and finally, grounding. Now, I really want to highlight 2 things here. First, the Canadian Solar 580 watt class panels. These are the absolute heart of our system, generating all that raw power. Second, look at number 9, grounding. Proper AC and DC grounding, along with bonding, is literally the ultimate safety feature protecting against electrical hazards. It is completely non-negotiable for safe, reliable operation.
Now, while those panels are the heart, the inverter is essentially the brain. Our source material focuses heavily on the Growatt Mod 10000 KTL3-X. It's a 10 kilowatt on-grid inverter, and it acts as the grand translator for the whole operation. You see, solar panels produce direct current, or DC electricity, but your home and the broader utility grid, they run on alternating current, or AC. So this Growatt inverter takes the raw DC language of the sun and seamlessly translates it into the usable AC language of your home and the grid. Pretty cool, right? Moving right along to section 2, doing the solar math. This is where we fit all the pieces together. Now, what's really interesting here is that you can't just plug any random number of panels into an inverter. It's like a high-stakes puzzle where the panel outputs have to fit perfectly inside the inverter's limits. On one hand, we have the Growatt inverter limits. It can handle a maximum PV power of 15 kilowatts, so 15,000 watts, and it operates within a voltage range of 140 to 1,000 volts. On the flip side, we've got the exact standard test condition, or STC specs, for our Canadian solar panels. They output 585 watts each with an open circuit voltage of 52.4 volts, an optimum operating voltage of 43.3 volts, and a short circuit current of 14 amps. We use these precise numbers to size our system safely. So, the big question, how many panels can we actually use? Well, if we take our inverter's maximum input power of 15,000 watts and divide it by the panel's 585 watt output, we get 25.64. And since you obviously can't install a fraction of a panel, this safely resolves to a maximum of exactly 26 panels for our setup. Having 26 panels is awesome, but we definitely do not wire them all into one giant loop. Instead, we divide them up into 2 separate strings of 13 panels each. Why? Because our Growatt inverter actually features 2 maximum power point trackers. That means it can optimize the power output of each string completely independently. It's a lifesaver if one part of your roof gets shaded while the other is still soaking up full sun. Let's just double-check the math to make absolutely sure this is safe. We take our 13 panels, multiply them by the panel's optimum operating voltage of 43.3 volts, and that gives us 562.9 volts per string. Now, if you remember our inverter's limits from just a minute ago, it handles between 140 and 1,000 volts. So at roughly 563 volts, we are sitting incredibly comfortably right in the sweet spot of the inverter's range. All right, section 3, wiring the DC side, building the bridge from the roof. So narratively speaking, we're building the first half of our electrical bridge, bringing all that raw power from the roof down to the inverter. That power first flows right into the DC distribution board, or DCDB. Think of this as our critical safety checkpoint. It houses the DC isolator switch, which lets you manually cut the power from the solar panels in an emergency or if you need to do maintenance. But here's a vital takeaway. DC systems are highly polarity sensitive. If you accidentally reverse the positive and negative wires in this box, no way around it. You will severely damage your expensive equipment. So always double check your connections.
And this brilliantly illustrates what's going on inside that distribution board. You've got two main protective layers, the MCB and the SPD. The miniature circuit breaker, or MCB, is there to protect your circuit from overcurrent and short circuits. Simply put, if too much power flows through, the breaker trips. The surge protective device, or SPD, well, it does a totally different job. It protects the entire system from massive, sudden voltage spikes. Just picture it as a bouncer that violently kicks out localized power surges, like tiny, stray lightning bolts, long before they can fry your inverter.
Okay, let's defang the math on how we actually size these two protectors. For the MCB, we take our panel's short circuit current of 14 amps and multiply it by a standard safety factor of 1.56. That gives us 21.84 amps. According to our source's sizing guide, if we round that up to the nearest standard breaker size, we get a 20 amp DC MCB. Simple enough, right? Now for the SPD. We take that 52.4 open circuit voltage per panel and multiply it by our 13 panels, coming out to 681.2 volts for the whole string. But we want a really solid safety buffer, so we multiply that by 2 for our recommended SPD rating, getting 1362.4 volts. Rounding that up to the next standard size means we need a 1500 volt SPD.
So what exactly is the physical connection sequence inside that box? Well, it flows like this. The wires from the roof first hit the isolator switch. From the isolator's output, they route directly into the input of the DC MCB. Next, the wires run from the MCB output over to the SPD, which is wired in parallel and, this is crucial, connected to the grounding system's earth bar. Finally, the clean, protected DC power flows out of the MCB and right into the positive and negative PV inputs on the solar inverter. And just like that, the first half of our bridge is completely built. Moving into Section 4, connecting the AC grid, meeting in the middle.
Now it's time to build the second half of our bridge, starting all the way from your local utility grid to meet the inverter right in the middle. So the crucial point here is that a 10 kilowatt system almost always requires a 3-phase grid supply. Unlike a standard single-phase residential plug you'd use for your TV, we're working with 4 distinct wires from the grid: phase R, phase Y, phase B, often referred to as L1, L2, and L3, plus a neutral wire. It is absolutely vital that these phases are matched perfectly when connecting them from the grid supply over to your energy meter.
Let's map out the entire AC sequence. Just like our DC side, it has a very specific logical flow. The 3-phase power comes from the grid straight into the energy meter, so we can measure consumption. From there, it flows into a 4-pole 100-amp AC disconnect switch, then into a voltage protection relay. Now, this is a fantastic safeguard. It disconnects the system entirely if the local grid voltage fluctuates dangerously. From the relay, power routes through the AC SPD to catch any surges, then into the appropriately rated AC MCB, and finally, directly into the AC output terminals of our Growatt inverter. And boom, the bridge is fully connected.
But hold on, before anyone even thinks about flipping the switch to turn the system on, there is some rigorous finalization required. Every single connection we just talked about must be securely tightened to the exact torque specifications provided by the manufacturers. You have to verify the voltage at various test points, check the operation of your relays, and ensure the entire installation strictly adheres to your local electrical codes. There's no cutting corners here.
And that brings us to the most critical takeaway in this entire explainer. Working with mains electricity is extremely dangerous. All electrical work should be carried out by a qualified and licensed electrician, period. Look, understanding the blueprint, the math, and the wiring sequence totally empowers you as a homeowner or an aspiring professional. It's great knowledge to have. However, incorrect wiring on a system this powerful can lead to severe property damage, serious injury, or worse. Always rely on licensed professionals for the actual hands-on installation.
By truly understanding the inner workings of a 10 kilowatt system, from sizing those Canadian solar panels to wiring the Growatt inverter safely through the DC and AC protection boards, you aren't just buying hardware, you're actively taking command of your energy production. You know the math, you know the safety steps, and you know exactly how the grid connects to your roof. So looking at your own home and your own energy needs, are you ready to take charge of your energy footprint?
Thank you so much for focusing in with me today on this explainer, and definitely keep exploring the incredible potential of solar energy.